Hello and welcome. In today's video, we're going to explore one of the most revolutionary concepts in machine learning and artificial intelligence, transformer architecture. If you've ever heard terms like BERT, GPT, or T5 in the world of AI, you've encountered models built on transformer architecture. Transformers have transformed natural language processing, NLP, powering everything from chatbots to machine translation. But what makes transformers so special? Let's dive in and find out. At its core, the transformer is a type of deep learning model designed to handle sequential data, like text. The transformer was introduced in a 2017 paper titled Attention is All You Need by Vaswani et al. Before it became the foundation for most modern NLP models. What makes transformers unique is their self-attention mechanism. This means that instead of processing words one by one in sequence, like older models such as LSTMs or GRUs, transformers can look at the entire sequence of words at once. This allows them to capture relationships between words, regardless of their position in the sentence. To understand the self-attention mechanism, let's use an example. Imagine you're reading the sentence, "The cat sat on the mat." The word cat is linked to the word sat, and both are connected to the word mat. In traditional models, the word cat would be processed in isolation, and the model would have to look back at previous words to understand the full meaning. Transformers, however, can look at all the words in the sentence simultaneously. This parallel processing is much faster and allows the model to learn relationships between distant words, like cat and mat, without struggling with long-range dependencies. The self-attention mechanism allows the model to assign different weights to different words in the sequence based on their relevance. For example, the model will focus more on the connection between cat and sat, while it might give less attention to the word the. Now, let's break down the main components that make up the transformer architecture. Firstly, the transformer is built on an encoder-decoder structure, where the encoder processes the input data and the decoder generates the output. Let's look at each part in detail. The encoder is made up of several layers, and each layer consists of two key parts. The self-attention mechanism we just discussed, which allows the model to weigh different parts of the input sequence. A feed-forward neural network, which processes the output from the self-attention layer and produces the final representation. Next, the decoder also has layers similar to the encoder, but with an additional feature. In addition to self-attention and feed-forward networks, the decoder has a mechanism that helps it focus on the encoder's output. This allows the decoder to generate the output based on the input sequence, which is particularly useful for tasks like translation. We've already touched on self-attention, but let's get into a little more detail. In self-attention, each word in the input sequence is transformed into three vectors. Query, Q, represents the word seeking information. Key represents the word's potential to provide relevant information. Value, V, the actual content or meaning of the word. By comparing the query vector with key vectors, the transformer determines which words are most relevant and assigns weights accordingly. These weights then adjust the values, helping the model decide how much attention to pay to each word. A key challenge in transformers is that they process all words simultaneously, which means they don't inherently know the order of the words in a sentence. This is where positional encoding comes in. Positional encoding adds information about the position of each word in the sequence, allowing the model to understand the order of words. Positional encodings are added to the input embeddings, ensuring the model knows where each word falls within the sequence. One of the major advantages of transformers is multi-head attention. This involves running multiple attention mechanisms in parallel, allowing the model to focus on different aspects of the input simultaneously. For example, one attention head might focus on syntactic relationships, like grammar, while another might focus on semantic meaning, like word meanings. The outputs of all these attention heads are combined, providing a richer understanding of the input data. Now that we've covered the basics, let's look at why the transformer architecture is so powerful. 1. Parallelization. Unlike older models like RNNs and LSTMs, transformers can process words in parallel. This means they are much faster to train and can handle larger datasets efficiently. 2. Handling long-range dependencies. Because of self-attention, transformers can connect words from different parts of the sentence, no matter how far apart they are. This makes them especially useful for tasks where context from earlier in the sentence is important for understanding later parts. 3. Scalability. Transformers scale extremely well with data. As you add more data and layers, the model can improve its performance without running into the diminishing returns that other architectures face. So, where are transformers used today? Well, pretty much everywhere. The most famous transformer-based models include BERT, bidirectional encoder representations from transformers, used for tasks like question answering and text classification. GPT, generative pre-trained transformer, used for text generation, chatbots, and language modeling. T5, text-to-text transfer transformer, used for a wide range of tasks by converting every problem into a text generation problem. These models have achieved state-of-the-art results in many NLP tasks, making transformers a go-to architecture for modern AI systems. To wrap up, the transformer architecture has completely revolutionized how we approach machine learning, especially in natural language processing. Its ability to process data in parallel, capture long-range dependencies, and scale efficiently makes it the backbone of most modern AI applications. Whether you're working on language translation, text generation, or even image captioning, transformers are at the heart of it all. We hope you found this breakdown of transformer architecture insightful and clear. To dive deeper into the transformer architecture, you can check out our course on mastering generative AI. Simply sign up or sign in at www.myCareerNext.com. Next, create your profile to personalize your learning experience. Then navigate to the Explore tab and select Trainings. And finally, you can enroll in the course Mastering Generative AI and take your skills to the next level. At myCareerNext, we're not just a learning platform, we're your career partner, guiding you from day one of learning to landing your dream role in AI, ML, and emerging tech. Our unique Career Enhancement Plan, CEP, provides a personalized, step-by-step roadmap with trainings, assessments, hands-on projects, mock interviews, and coaching that surpass the rigor of traditional master's or PhD programs. With our AI-powered platform, you'll receive real-time pros, bias-free feedback to keep you on track and future-proof your career. And at myCareerNext, we also ensure that you stay ahead of the curve with all the job-ready skills that employers demand. So join thousands of professionals on a seamless journey of endless learning, earning, and career growth, only at myCareerNext.